particulate matter, and that has to be collected and cared for. But we don't waste anything here. We're going to collect this gas and use it over again if we can. We say we have a waste product, which is slag. And out of this particular mix, it says we get about 30 tons of slag out. Although it's a waste product, if you're trying to produce steel, it turns out to be a very good product. And it's called blast furnace slag, and we use it all the time. We use it in road ballasts. We use it as aggregate in concrete. A lot of what you call cinder blocks, the cinder in it is going to be blast furnace slag. It's a porous mass that comes out that we can use. And actually, we operate the blast furnace to produce the optimum chemical composition and mechanical property slag balanced with the optimum composition of the material, which is going to be called pig iron that's coming out. I find that a lot of people get confused about the difference in the names that the metallurgists use, and sometimes we get confused ourselves. But the word pig iron has stuck with us over the long centuries. And the name came from the fact that in the early blast furnaces, which were just shafts or stacks in which we piled all this material and blew the air through it to get the high temperatures, when we got ready to tap, the material was actually contained in the bottom of the furnace in a collecting hearth known as a crucible. And we wanted to get the material out of that crucible. We went up to the crucible and tapped a hole in it, or picked a hole in it, or bored a hole in it. And you can imagine the job this was in the old days when somebody had to literally shovel the material out of a little track that's going to lead to where the material is incandescent on the inside. And finally we'll blast through a hole, pick through a hole, and the molten iron will come running out of the blast furnace, but now you have to do something with it. So they conducted it down little sand valleys, little tracks in the sand, and then had rivulets that would go off the side into larger swollen sections. And someone looking at that says, gee whiz, that looks like a bunch of pigs nursing a sow. And so they call these little ends, the little castings that they made, pig iron. And it has stuck with us from that day to this. We call the material out of the blast furnace pig iron. But it really is cast iron. It's the material that I described to you before with a slight modification. Well, we take this particular material and we could use it as cast iron if we wanted to. But if we're interested in making this cake, which says we want to wind up with steel, we can run it into a number of different processes. But shown here is a basic open hearth furnace, which is nothing more than an enormous bathtub. It has ports on either end in which we can introduce a fuel that we can cause to burn in a very hot manner. And the way we do that is we pass the incoming air that's going to mix with that fuel. We pass it over hot bricks. Now, hot bricks are made hot by the gases that come out of the open hearth furnace, passing over a bunch of bricks, heating them up, and after they get hot, we cause the air to run over those, and when that's happening, on the other end of the furnace, we're heating up another bunch of bricks. It's called a regenerative system. So by having hot air to blow, to mix with the gas and burn it, we can get very high temperatures, and we get temperatures high enough to melt steel. Well, do we just put pig iron in the steel? No, we don't. We could, but we don't. Because we have coming back in this industry all of the iron scrap, all of the steel scrap and iron scrap. And so we charge into the furnace steel scrap, and we are going to have to do a refining operation, because now we have carbon in the steel, just like this early man had it when he wanted to mix his iron oxide with it. We're also going to mix iron oxide with it, but in a furnace that's big enough so that we don't have to rabble the material in, and we can have an enormous amount of material, 200 tons of material or something like that. And so the iron ore is fed in with the steel scrap, and we also put limestone in it, and the limestone primarily is to make a flux, a slag that will float on the top, will be relatively fluid, and the iron oxide establishes an equilibrium in the steel. Iron oxide will dissolve in the cast iron or in the iron-based material. And so as it dissolves and the oxygen now chases around in this molten material, it sees a little bit of carbon, combines with it, and percolates off as carbon dioxide. And so if you were to look in an open hearth furnace, well, number one, you would really be looking at something horrendous. I mean, you feel like what I imagine it's going to be go to hell. You'll have a lot of metallurgists down there, I think, but they're used to this. But you look in this furnace, which is incandescent now. You have to look through cobalt glasses, and the material looks like it's boiling. You see all of the bubbles coming out of it, and you say, gee, they've gotten a temperature high enough to boil the iron. They do not. What you really see is the percolation of the gas out of the material, right? Well, finally, you decide that you've gotten enough carbon out of it. I'm going to show you how in a moment. But when you decide you've gotten enough carbon out of this, then you tap the furnace. And again, somebody's got to crawl up into this cavity, chiseling the material out, and finally he gets right next to the bottom of the hearth. And the bottom of the hearth, we're going to have now an incandescent ceramic material, a brick material. And that has to be picked out. It used to be that people would go in there and take rods and jam them into that until they blasted a little hole in it. And then as the molten steel comes running out, it enlarges the hole. And then we got so we could do nicer things, and we take a long rod of iron, iron pipe. We'd hook an oxygen tank on the end of that. We'd heat up the iron pipe just by running it up this channel. And when it got next to the melt, it would heat up. We'd open the oxygen tank, and as the oxygen would run through, it would see the iron and oxidize the iron. And the heat of oxidation of iron is tremendous. It's so hot that it would melt the bricks in front of it, and we could melt a hole in it. So now you could stand a long way back and fish this pipe up there and melt the brick, and then the whole cascade of 200 tons of iron come rolling out of the furnace, and you got to catch it in something. And so what we do is we catch it in a teaming ladle, which we'll look at, and we can get iron that's very pure to come out of the material. We could get a 99% pure iron. That means 1% carbon. Actually, we can operate the basic open hearth furnace so we can get pure iron, a relatively pure iron, called something like Armco ingot iron or something like that. Or we could have steels of any carbon content we want. But once you do this, it comes out with a rush. And you have 200 tons of steel, let's say, and you got to collect it. And so they put it in one great big cup called a teaming ladle. And then from that teaming ladle, we cast it into steel ingots, or we do other processes with it directly. Now let me see if I can give you an idea how fast we've changed. About 1942, in a steel mill, on a modern steel mill, let's say we're in the Second World War and we're trying to produce everything as fast as we can, we could refine about 200 tons of steel in an open hearth furnace in about 13 hours. It would take 13 hours to make it into steel. By the end of 1943, we could do that same job in about 6.5 hours. And today we have a process called a BOF in which we can do that job in about 15 minutes. So we've moved rapidly in our capability of this refining. And of course, most of this has been made possible by new designs, electronic control of the systems and things like that. But that's the flow that we would have as we're going through the steel mill now to try to make this cake. And the cake is down here, and it's called the steel ingots. And if we started out putting these amounts of the material in, we'd find out that we'd wind up with a cake that's about 100 tons of steel. Yes, sir.
What do you make such a furnace out of? And all these ladles and all sorts of things like that. It seems like, I mean, the obvious thing to make stuff out of is steel, but obviously that isn't going to work in this case.
Well, the answer is yes, it does. We depend upon the steel for strength, but we have to put something in there that won't melt. I mean, that's obvious. So we're looking at things that won't melt above the melting point of iron. And when you do that, you find that if you wanted a metal to put it in, the highest melting point of a metal is, say, tungsten. It has a melting point of approximately 6,100 degrees Fahrenheit. And there's nothing to hold molten tungsten in except itself. Or carbon. Carbon doesn't have a melting point anywhere near that. It's way above that. But if you put tungsten in carbon, you get tungsten carbide. So you run down the scale and you finally find that you have refractory materials like magnesium oxide. And magnesium oxide has a melting point of something in the mid 5,000 degrees, like 5,400 degrees Fahrenheit. So the open hearth is lined, a basic open hearth furnace is lined with magnesium oxide. But there has to be something to hold up to 200 tons. So on the outside of the magnesium oxide is a steel shell, a mechanical shell, a support shell to hold it. Same thing is true in the ladles. the ladles are going to be lined with something like magnesium oxide. But the ladle itself, the strength part of the ladle that stays approximately at room temperature, the thing that's on the outside, is going to be steel.
Do you have to cool it?
No.
With something?
No. No, you put enough refractory in there. You don't have to cool it. You put enough refractory in the ladle so that the temperature drop is sufficient so that the convection currents of the air keep it cold enough to maintain the strength and keep it all together.
What did they do in 1850 or 1750 when they were making steel?
Well,
I mean, were they really using things like magnesium?
one of the you notice what if you want to look at what the ancient man did, you notice that I said he couldn't handle big quantities, so you didn't need the mechanical strength to hold everything together. So if you need a little small pot to hold it together, you can just make it out of the fire brick itself or the refractory material. And even today, when we melt small amounts of material, we don't have a ladle that has steel on the outside. We just have a fire clay graphite bonded crucible, and we can melt material because it's not a big mass inside that we have to handle. Okay? Well, if we look at the first slide now, we will find that we see what goes on if you happen to be a melter in an open hearth and you say, I want to make this cake. But now the cake I want to make is to prescription because somebody out there wants this steel. And they have ordered the steel through the order department in the steel mill. They said, I want a carbon content that is a certain value. And let's suppose that the carbon content is indicated at, say, about less than 1%, say 0.5% carbon. And this is the content that's ordered. And that's what the melter has to hit. What he does is, he gets this pig iron, which has a carbon content way up here, and in his open hearth furnace, he's reducing that carbon content so it becomes lower and lower and lower with time. Now what you see I have here is a 12-hour time period out here, and so what it would say if he plotted this thing, and he keeps taking samples and plotting it, and he says, he's at this point in time, let's say at 5 hours, and he looks at it and he says, I know I can extrapolate that curve, and at 3:33 this afternoon, I want to tap that furnace. All right? And so he taps the furnace at that particular time, and then the reaction should stop. Does the reaction stop? The answer is no, it doesn't. Because in his whole operation now, he has put iron oxide in the system, which is dissolved in the iron, and it takes time for the cake to cook. So the iron oxide is reacting with the carbon continuously, and when it's tapped out of the furnace, he still has iron oxide mixed with the material. And it's still going to effervesce, give off the gases. So if you looked at this ladle with 200 tons of steel in it, and you look down in it, you'd find out, gee, on top of it's going to be some slag, and through the slag is going to be all of this gas percolating and bubbling, and it looks like it's wild. And so we have to stop that action right there. Otherwise, we're not going to have the right carbon content. So one of the things that we do is we throw into this in pre-weighed bags for the amount of material we have. We throw in bags of manganese compound, let's say a ferromanganese alloy. But a specific amount of manganese will go in the heat. The manganese has a greater affinity for the oxygen than the carbon does. And so it will grab up the carbon and become manganese oxide, which is a solid state material, not a gaseous material. Or it will be a liquid state at that temperature, but it doesn't go off as a gas. But it stops the reaction. We say it kills the heat. And so when you order a killed steel, then you're ordering a material that has been killed with manganese. So you have manganese killed steels, silicon killed steels, aluminum killed steels, and